is the difference in calculating gravitational potential energy with mgh versus the correct calculation of the constant of gravitation, capital G, multiplied by the two masses and divide by the distance from center to center of the two objects. So we're going to relate this to at the Earth, problems at the Earth. And using mgh, m is the mass of the object, g is acceleration due to gravity, and h is the distance above ground level. Usually we pick h to have a value of 0 at the surface of the Earth. Again, with potential energy, you can set the 0 point at any place, and as long as you're consistent in your distance labelings, you'll get the correct answer. The 0 point is not important. It's the change in potential energy that gives you the correct result to a problem. So we're going to work this with h being the vertical distance above the surface of the Earth. And the question in this video is, what is the value of h that occurs such that mgh is too big by 10%? It's 10% too large. And really the problem comes in here when we're doing mgh, and h is a large number above the surface of the Earth. This acceleration due to gravity is not a constant. Small g has a value of 9.81 meters per second squared at the surface of the Earth. But as we go away from the center of the Earth, the force of gravity becomes weaker. The acceleration due to gravity becomes a smaller number. So we're going to use mgh on one side of the equation here, and to represent 10% higher than the correct change in the potential energy, I'm going to put in a 0.1. That 0.1 is the 10%. The correct change in the potential energy is to do the correct calculation for potential at each location, the potential energy at each location. So capital G, the mass of the Earth, the mass of the object, divided by radius of the Earth. That's for the object at the surface of the Earth. And then when the object is a distance h above the surface of the Earth, we add in the h to r sub e. So first simplification here to take a look at, there's m in every term, so you can divide both sides of the equation by m. Whatever object that was, it doesn't matter, a car, a marble, that's canceled off. Next, I divide by 9.81. So 1.1 divided by 9.81, we get this, this value. Next, I'm going to multiply every term by the quantity r sub e plus h. Multiply every term. So this term's going to get multiplied, this term's going to get multiplied, and the h is going to get multiplied. So here we have the re plus h factor on the left. I didn't write down every step of the algebra process here, but if you want to think of it, first distribute the 0.112 on both terms, and now multiplying both terms by r sub e plus h. That is represented here. Why isn't r sub e plus h multiplied on this term? Well, because it's canceled, the r sub e plus h in the denominator. So just leaving us the 0.112 times g me, and that's a negative value. Going a step further, distributing h through here, and on this side distributing in the parentheses here the re plus h. So when this first 0.112 g me re is done, that multiplication, there's an re in the denominator, so that is canceled off. So leaving us the 0.112 g mass of the Earth. And then the second term that's created, 0.112 g me times h, that still has division by r sub e, and then this term has just been repeated. If you take a look here, I've got a positive quantity, 0.112 g me, and I have a negative term of a like term, g and me, so those add to 0. So we just get this middle term on our next line. And now another simplification. I'll ask you first before I reveal it. What would be a logical next step? Dividing everywhere by h. So divide by h, reduce the power by 1, h disappears here. And again, we're interested in solving for h, so the next step is to subtract r sub e from both sides. And now I'm going to go ahead and put in the numbers, as we've got values for the universal constant of gravitation, for the mass of the Earth, the radius of the Earth. Go ahead and put in those numbers. You should pause at this point and do the calculation yourself. Welcome back. So that first term is 7 times 10 to the 6. Do the subtraction, and we find that h is 0.62 times 10 to the 6 meters, or 6.2 times 10 to the 5th meters, or if you prefer, 620 kilometers. That's the value of h, where mgh is in air by 10%. If you're in the United States, if you want to discuss this in miles, converting the meters or the kilometers to miles, you get 385 miles roughly is the value of h. So in textbook problems where we're doing an amusement park ride or a ball rolling down a ramp, h is much smaller than 385 miles, and you're okay in using mgh. But if you get to low Earth orbit and beyond, then you better use the correct version of potential energy. G, m sub e, the mass of the object, and then the distance between their centers. Again, h is only the distance from the surface of the Earth to the object. And last comment, this is around 10% of r sub e. So we looked for a case when mgh was off by about 10%, and that turns out to be about 10% of the radius of the Earth. So ask your instructor if you have questions with this, but that's an illustration that mgh is not perfectly accurate. At a height of 620 kilometers, mgh is too big by 10%.